In this video, we're going to look at exactly how an atom forms a covalent bond with another atom. We understand this idea that when a bond forms, energy is released. It's favorable for an atom to form a bond, otherwise it wouldn't happen at all. So the driving force for chemical bonding is the fact that the atoms involved in the chemical bond reach a lower energy state. So if we think about how exactly these orbitals overlap to form bonds, there are two theories that can be used to describe bonding in a molecule. One is valence bond theory, and this is the simplistic view that a bond is the overlap of two atomic orbitals. So here, say I have two hydrogen atoms. They each have a 1s orbital. Now, I got crafty and cut out some circles from poster board, and these are only two-dimensional. But remember that the 1s orbital is a sphere, so it's more like a ball. But for my purposes here, these will be easy enough to bring together to show that this overlap of the atomic orbitals forms a covalent bond. And in this case, this would be a specific type of covalent bond, a sigma bond. So we'll define that in a second. But as these two atoms come closer and closer together, they reach an energy minimum. And that energy minimum is the bond distance, the bond length between the two nuclei. If those nuclei get too close, then we have a disfavorable interaction because we start to get repulsion between the two positively charged nuclei. So it's this perfect balance between essentially three forces that determine how long the chemical bond will be. Let's take a look at the plot over here. We have potential energy on the y-axis, and we'll have a low energy being negative values and high energy being positive values. We have our 0 mark here, and on my x-axis I have the distance. Could be denoted as an r here to indicate the radius, the distance between these two atoms. So when these atoms are sufficiently far apart, there's essentially no attractive or repulsive forces between them. And that would be at energy of 0. And at least we would approach 0. They'd have, at infinity is where we would have potential energy equal to 0. So when these two atoms are far apart, we have an energy that is approaching 0. As they come closer and closer together, we start to get electrons in one of the atoms attracting to the nucleus of the other atoms. And so that attractive force becomes favorable. So we start to dip down in energy here. As they get closer and closer together, we get to an energy minimum, right? And this energy point would be the bond length. For the hydrogen bond, that is 74 picometers. So it's a very small number. But then as those nuclei get even closer together, we start to get some of those repulsive forces. I mentioned the repulsive force between the two nuclei that are positively charged, so that's a downside. And then the electrons are also going to repel one another as well. So we start to get an increase in the potential energy, and it will approach a maximum as we get to the point of 0 here. So we have this bonding distance here, which is the ideal distance, and then at this case they are essentially too close together that they are at such a high energy because those repulsive forces have now taken over and become more significant than the attractive forces of the electrons in the two nuclei, or in the two atoms to the other nuclei. So it's important that we understand that bonding is energy releasing. We're going to be at a low potential energy, and that is a favorable situation. Okay? So those three forces again, we have the forces of attraction between the electrons and both nuclei. So the one electron in each atom is going to be attracted to the nucleus of not only itself, but of the other atom as well. And then we have the repulsive forces of the two nuclei and the repulsive forces of the electrons with other electrons. There are two types of covalent bonds. One is known as a sigma bond, and the other is a pi bond. Let's first look in detail at a sigma bond. So a sigma bond occurs between two atoms and is the overlap of atomic orbitals. So we call this end-on end overlap or head-on overlap. So while these s orbitals would be spheres, we can imagine that as those spheres come together, they begin to overlap. This is the case as we've been looking at. So if we're talking about hydrogen and hydrogen, the one s orbital from hydrogen and the one s orbital from the other hydrogen will overlap constructively to form a bonding region. And the sigma bond is cylindrically symmetric about a bonding axis, so most of the electron density is here on that bonding axis. Another type of sigma bond is that between an s orbital and a p orbital. So they could overlap constructively to form a sigma bond, again with the head-on overlap. Notice that my p orbital has two distinct colors here. And these colors are indicative of the phase. So remember that an orbital is characterized by a sine wave, or by a wave function, and we can compare that to a sine wave. Sine waves exist above the axis and below the axis, so they have a positive phase and a negative phase respectively. And this is in no way correlated with a charge, so I just want to make that very clear. So when we look at my p orbital about the axis, we may have a positive phase, we will have a positive phase and a negative phase. And in models, we indicate those different phases by different colors. And in kind of these pictures, we could use different colors, or we might use shading. So one lobe might be shaded and the other may not. So that's another way of indicating those differences while you're drawing them. So we must have like phases come together in order to form a constructive overlap here and a bond. If we look at how this can be drawn in terms of two atoms, there's my nucleus and here's my electron as a wave. If that comes together with another nucleus with electron in the same phase, we will get constructive interference, and that would be a bond. If we have a wave that is coming together with the opposite phase, then this is not going to have any constructive interference. It's actually destructive interference, and this would be no bond. So the s orbital and the p orbital can come together constructively, but not destructively. Okay? Another type of sigma bond that we can have would be the overlap of two p orbitals. We can form a sigma bond, again cylindrically symmetrical about the bonding axis, and this constructive overlap of the two identical phases coming together. The second type of covalent bond is what we call a pi bond. And a pi bond, by definition, is the side-to-side overlap of atomic orbitals. So we have two p orbitals coming closer together. They overlap above and below the bonding axis. And because there are nodes here at the axis, there's zero probability of having electron density there. So we actually see a node in the bond as well. So we have these two p orbitals coming together, and we can draw the bond as such. This is the overlap of the top region. Here's my bonding axis, and then here's the overlap of the bottom region. So we end up with electron density above and below the bonding axis, and this constitutes one pi bond. And you can remember the name pi from p, okay? So pi is the Greek letter for p. So in this course, we are going to almost exclusively be looking at the overlap of p orbitals as the only example of a pi bond. So the side-to-side overlap of p orbitals is weaker than that end-on-end orbital overlap. So pi bonds are always weaker than sigma bonds. And in compounds, the pi bond will always be the second or third bond. So in, say, ethane, the carbon-carbon single bond here will be a sigma bond. And if there is only one bond, it is always sigma. When we have two bonds between atoms, there will always be one sigma and one pi. The first bond is that sigma bond. The second bond is that side-to-side overlap of p orbitals. And finally, when we have three bonds, there will be one sigma plus two pi bonds. And these pi bonds will be perpendicular to one another. So we'll have the overlap in one direction, and then we'll have side-to-side overlap in a perpendicular plane to form those pi bonds. And we can see pictures of that here. So that is sigma and pi bonding. Note that a single bond is always a sigma bond, and that double and triple bonds will have one or two pi bonds respectively. Thanks for watching.